since our shortest paths tree algorithms like Dijkstra's are not going to work for minimum spanning trees, we need something else. So what I'm going to use is something called the cut property. It's a really beautiful, simple idea that is a little surprising that it works, as we'll see in a moment, but it'll allow us to compute minimum spanning trees in a bunch of different ways, all resting on the foundation that is known as the cut property. So the basic idea here, I'm going to first introduce a term which is a cut, which is an assignment of a graph's nodes to one of two sets, right? So, and as an example here, we have a graph, and I've decided some vertices are gray and some are white, and it's just totally arbitrary which ones I pick. Second term I'm going to define is a crossing edge. So a crossing edge is any edge which connects vertices from the gray side to the white side. Now here's the surprising fact that the cut property tells us. If you make up any cut, anything you want at all, you just decide arbitrary, you're gray, you're white, the smallest edge amongst all of those which cross the cut is guaranteed to be part of the minimum spanning tree. Okay? So let me see if that makes sense. I'll give you a chance, then we'll reflect on it a little bit. So to make sure that the property makes sense, I have here made up a new cut, which is that the vertices 2, 3, 5, and 6 are on the purple side, and 1, 7, 4, and 0 on the white side. Your job is find the minimum weight edge which crosses the cut, that connects a vertex on the white side to the purple side. And these here are the weights of each edge, which just happen to be proportional to the length of the line on the slide. So give that a shot. Okay, so hopefully you've thought about it. So we look at 0, 7 first. That, it has weight 0.16, but it is not a crossing edge. 2, 3, also not a crossing edge. 1, 7, not a crossing edge. But 0, 2, it is a crossing edge. And so what we know is that this is guaranteed to be part of the minimum spanning tree. And what I find surprising about that on first glance is I just made up the purple and white out of nowhere. It was just, flip a coin over and over. And yet, having done that, the minimum crossing edge is guaranteed to be part of the minimum spanning tree for the entire graph. And I think that's pretty extraordinary. Okay. So 0, 2, it must be part of the minimum spanning tree. So why does this work? Where does this, how do you show this? Well, it turns out there's a pretty simple, cute proof where we just prove by contradiction. So let's suppose that you come up with an arbitrary cut and you find the minimum crossing edge, and let's suppose it was not in the minimum spanning tree. Well, in that case, because, we have a thing that's the minimum spanning tree here, right? There already existed some minimum spanning tree. If we were to add E to the minimum spanning tree that E is not a part of, because we supposed that at the beginning, well, once we add E, we now have a cycle. Why? Well, the reason there's definitely a cycle is this used to be a tree that connects all the vertices. It was fully connected. And so if we add another edge, because everything was already connected, there must somewhere be a cycle. And what that means is that somewhere else, there had to be a crossing edge already, right? Because we had some set of vertices that were gray, some that were white. So there must be some edge that connects them because the spanning tree is always connected. So we have basically a redundancy here. There was an old spanning edge. We've now added a new spanning edge. And what's interesting is that by the definition of our made-up scenario, E has lower weight. And so what we could do is just remove F, the old crossing edge that E is redundant with, add E instead, and it makes a new, better minimum spanning tree. So that's a contradiction. So what we can say then is that the minimum spanning tree must include E. I think this is a really cute proof. Now this is a topic in general, the cut property, that doesn't often appear in a data structures course like CS61B, but I think it's such a cool idea that rather than waiting till you get to an algorithms class, I'll tell you about it here. So now that we're armed with this really powerful property, the cut property, we can start developing some specific algorithms that'll let us compute a minimum spanning tree. So for example, one algorithm might be, okay, we start with no edges in the minimum spanning tree, and then we find any old cut, just randomly flip coins so that some vertices are white and some are gray. And once we've found the cut that has no crossing edges that are in the minimum spanning tree, then we add the smallest crossing edge, and then we just repeat that process over and over until you end up with the minimum spanning tree. So you're just brute forcing your way through using the cut property. Make a random cut selection, maybe, then pick the minimum spanning, or the minimum weight edge, put that in the minimum spanning tree, and just repeat that until eventually you have u-1 edges. Now the random approach isn't going to be nearly as good as the better approaches we'll describe in a moment, and so we'll see that there are more intelligent ways to do this first tricky step, which was to find a cut that has no crossing edges. So we'll do that in the next video.